In this video, I am going to give you an overview of stoichiometry. What it is, how you do the problems associated with it, why you need certain steps, that kind of thing. Now, stoichiometry, one of the first questions we get is, what does that word even mean? Because it is kind of a weird word. And not that you need to know this, but it ends up being a combination of two ancient Greek words. And the first one, and I'm probably pronouncing this wrong, is stoichion. That's how it's spelled, which means element. And then metron, which really just ended up becoming like geometry, like measure up stuff. Alright, so that becomes measure. So you put them together, you get stoichiometry. So it's measuring elements. It's giving you an idea that stoichiometry is all about quantitative data. It is numbers. And that's what we are going to end up doing with stoichiometry. Like I said, I want to leave out a lot of numbers just to give you a general overview of how it works. So I'm going to come up with this made-up equation. I'm going to put coefficients in there because they're important when it's balanced. Now, most stoichiometry problems are referred to as three-step problems, where I might give you, in this case, I'll just make an up number, like 10 grams of A, and it'll say B's excess. So it might say you have 10 grams of A reacting with an excess amount of B. How many grams of C are going to be generated? Now, this word excess, you don't really have to worry about that. Excess is telling you that this A, whatever this substance is the limiting reactant. Now, if you end up taking a higher level chemistry class, it won't tell you these things. You'll have to calculate which one's the limiting reactant and which one is in excess. So when you do a reaction, most of the time you don't have the exact amount of both reactants. One of them is going to get used up first. The one that gets used up first is the limiting reactant. So if you see the word excess in there, really what it's saying is you're going to start off a problem with that, in this case, 10 grams of A. So let's write that down first. 10 grams of A. Now, one of the things I want to get across in this video is that the heart of every stoichiometry problem is a mole ratio. Alright, so what we're going to have to do is figure out how to go from 10 grams of A to grams of C generated. Now, if you start off with grams of A, that's what will go on the bottom. Now, there's no conversion factor that lets me go from grams of A to grams of C. I can't do that. I need more steps. And what I said is at the heart of every stoichiometry problem is a mole ratio. So what I want to do is somehow convert grams of A to moles of A. And this is something that we have done several times. This is using a conversion factor. All right. When you're using the conversion factor, you're just changing the units, but it's for the same compound. So in this case, I'm going from grams of A to moles of A. So whenever I do this, the conversion factor, it's always going to be the number 1 with moles. And to figure out the grams, that is the molar mass. Right? You get that from the periodic table, and that's how many grams are in 1 mole. So grams per mole, so that per mole is telling you a 1 here. Now, grams of A are going to cancel out. What I'm left with is moles of A. So that's going to go on the bottom in the next step. Now, this is the mole ratio step, and this is what I said is at the heart of every stoichiometry problem. And this is a step that people forget a lot sometimes, like one of the most common parts that people forget. So what I can now do is look at this balanced equation, and it says for every 2 moles of A used, I'm going to generate 3 moles of C. So what I would do is 2 moles of A here, because that's the coefficient in the balanced equation, and 3 moles of C, because that's that coefficient. All right, so now what I have is I'm starting to get an idea of how much C is going to be generated. But I don't want moles as the answer. I want grams. So what I have to do is put moles of C on the bottom, so that cancels out, and I'm going to put grams of C up top. Now this is another conversion factor. Notice how it's the same compound or element. It's this C. And when you have the conversion factor, it's always 1 mole. Now in this case, it's talking about grams, so I would get that from the molar mass again. It's always grams per mole, so again, that's why it's 1 mole. So now when I do this, moles of C will cancel out. Now to do the math, what you would do is 10 divided by this molar mass, multiplied by 3, divided by 2, multiplied by whatever this molar mass would be, and that will be your answer. 10.0 is 3 significant digits, So I would write my answer in 3 significant digits or significant figures, whatever word you use. Remember, you never use the conversion factors or mole ratios to figure out significant digits. They are said to have an infinite number. Now, this is a very common example of a stoichiometry problem, and there are variations on this. So let's just say, for argument's sake, that this A, whatever it was, is not a solid. It's actually a gas. Now, what happens is it would start off with, instead of grams, it would start off with something like liters. Now, most of the problem is actually going to stay the same, but there are going to be some changes. So if we're starting off with liters, the conversion factor you would need is that in 1 mole of gas, and I don't care what the gas is, you're going to have 22.4 liters. It doesn't matter if the gas is a diatomic element, like oxygen is O2. It doesn't matter if it's something like carbon dioxide, CO2, where you have a couple different elements in there, or CH4, which is methane. 1 mole of any gas is 22.4 liters. So you start off with the liters of oxygen that's given in the problem, or liters of A, whatever it may be. You do the conversion factor using 22.4 liters as 1 mole. The mole ratio, remember, at the heart of every problem, what we wanted to do is go from moles of A to moles of C. What might change from one problem to the next is these conversion factors. It depends on what you're given. All right, now in this case, if C is a solid sample, you would just do the molar mass for C. Now, again, for argument's sake, let's say instead of C being a solid, let's say that is also a gas, and we want to know how many liters it would be. Well, most of this problem is the same. The only thing we have to change is this last step, and again, we would use that conversion factor of 22.4 liters is 1 mole of any gas. You start off with the 10.0 liters of A, you would do 1 mole is 22.4 liters of A, so liters of A cancel out. That mole ratio step hasn't changed because these coefficients are the same. So the only thing that would change is if C is a gas instead of a solid, is this last step. 1 mole of C is 22.4 liters of C. The idea behind it is still the same. So they're really the 2 main examples of what we would see as stoichiometry. Now, a lot of times teachers start off with easier problems, like 1 and 2 step problems. Let me rewrite some things here to explain that. So say we're working with this same made-up equation. A lot of times when people teach stoichiometry, they'll start off with a mole-to-mole problem. The easiest type of problem you can have for this. In reality, it's actually not very realistic because in the lab, there's no balances that give moles, but it gets the point across that you have to do this mole ratio step. And like I've been saying, the mole ratio is at the heart of every problem. So let's say you start off with a certain number of moles of A. How many moles of C are you going to get? Well, what you would do is you'd start off with whatever this number is in terms of moles of A. So let's just say you're given 2 moles of A. Well, remember, we want to go from moles of A to moles of C. This is very easy to do now. We do this mole ratio step. We know that for every 2 moles of A used, you get 3 moles of C. Label these. And moles of A cancel out, and then you'd be able to get your answer there. Again, it's not really all that realistic because balances do not give us moles. Now, this can vary a little bit. A lot of times teachers will then do 2-step problems. Well, let's say, well, if you're given 2 moles of A, how many grams of C are you going to get? Well, again, this stays pretty much the same because remember, at the heart of every problem is a mole ratio. Well, I'm already given moles here. So I don't have to do that first step like I did before I erased everything where I was doing grams to grams. If I'm already given moles here, I could just get right into that mole ratio. Now I put moles of C on the bottom here. I'm looking for grams. So now this is a conversion factor. It's moles of C to grams of C. It's the same element or compound. So since it's a conversion factor, I put the number 1 with moles. The grams you'd get from the periodic table, the molar mass. Moles of C will cancel out, and you'll be left with grams of C. Now another variation of this is instead of starting off with moles of A, you could be given grams of A and ask for moles of C. It's still doing the same general thing. It's just that these steps are going to be in a different order. And these are the things that really work up to what I started this video off with. But as long as you understand stoichiometry and you know what you're doing, it shouldn't really matter what's given and what's asked for. You should be able to set it up. So let's say you're given 2 grams of A, and we want to get to moles of C. Well, there's no conversion factor that lets me go from grams of A directly to moles of C. You can't do it. What we have to do is that mole ratio step. Remember, like I've been saying, mole ratio is at the heart of every stoichiometry problem. So what I want to do is make sure I compare moles to moles. So I start off with 2 grams of A. So I put grams of A on the bottom, and I convert that to moles of A. Since it's a conversion factor, number 1 goes with moles. I get the molar mass from the periodic table. Alright, so now I'm left with moles of A, but I don't want moles of A. So I put that on the bottom. I want moles of C. So it's every 2 moles of A will give you 3 moles of C. Alright, now moles of A cancels out, you'll be left with moles of C. Alright, now you can get more complicated problems depending on what level of chemistry you're taking or what your teacher's trying to get you to focus on. Let's just say, for example, your teacher wants to bring in something that's going to need Avogadro's number. So let's say instead of grams, let's say you're given a certain number of particles. Whether it's atoms or molecules or formula units, it doesn't really matter. And it wants to know how many grams of C you might get. Well, you would start off with every number of particles you have. It would probably be a very large number that would involve scientific notation. Well, remember, I don't care what you're starting with. You have to get to a mole-to-mole ratio. So I have to convert these particles to moles to be able to do that mole-to-mole ratio. So what I'm going to do is write the units of particles on the bottom. And we're talking about A. This is what we're starting off with, so I want to label that. I'm going from particles of A to moles of A. Well, this is the conversion factor, so it's always going to be 1 mole. Now for particles, this is where you would need Avogadro's number. Remember, in a mole of anything, you have 6.02 times 10 to the 23rd particles of it. Alright, well now that is getting me to the point where I have moles of A. So now I can do that mole ratio step, the thing that I keep saying is at the heart of every stoichiometry problem. So I can go from moles of A to moles of C. Again, just using the coefficients in the problem. Alright, now moles of A is canceling out. Now what I have is moles of C, but I don't want the units of moles. I want the units of grams. So moles of C goes on the bottom, grams of C goes up top. Since this is a conversion factor, it's 1 mole of C will give me whatever the number is off the periodic table, the molar mass in terms of grams. Now moles of C cancel out, and you can do the math. So a thing that people mix up a lot is when you have the conversion factor, it's always 1 mole going with whatever the unit is you're converting from or to. It's the mole ratio step that uses these coefficients up top. Alright, now if you end up taking a higher level class, you might end up doing what's referred to as solution chemistry. Now I'll talk a little bit about it, but at this point for the 5.0 level, we haven't talked about this yet, but that's okay. We can start off with something here. So let's just say you're given something, a liquid, and it has a molarity to it, like 6 molar. Like when we use acids, we might have 6 molar HCl or 3 molar HCl. So let's say you have 10 milliliters of a 6 molar solution. This molarity is just telling you how many moles are dissolved per liter. Alright, so if you have a 6 molar solution, that has more moles per liter than a 3 molar solution. So let's say you're given, it says you use 10 milliliters of a 6 molar solution, how many grams of C are you going to get? So what you would end up doing is start off with that 10 milliliters. And remember, at the heart of every stoichiometry problem is a mole-to-mole ratio. So you would start off with that 10 milliliters. Now, the next step, we're going to need that molarity. Because remember, molarity is how many moles are dissolved per liter. Like I said, for 5.0 Chem, we're going to get to this a little bit later. So this is jumping ahead some. So if you don't get this, it's not a big deal right now. What you would then do is, if it's a 6 molar solution, you would have 6 moles of A per liter, but notice the difference in units. So instead of writing 1 liter, I'm going to write 1,000 milliliters, because now I know my units are going to match up. And then once you have that, you can run through the rest of the problem. Milliliters cancel out. You'll have moles converted to moles of C, and you'll be able to get the grams. Right? So just a lot of different variations, but they're all set up the same way.